So congratulations, you have passed your first mastery check, hopefully if you are watching this, and you are on to section 1.2 where we will be modeling with graphs. So we talked about Professor Splash last video. He set the world record with that 36-foot belly flop into the 1-foot pool of water. Here's the graph we ended up coming up with. If you look now, we have added an equation, and we can use our equation now to fill out our t-chart. Last section, we just used points in the graph, and there's nothing wrong with that. If we would have just used the points in the graph, at time 0, his height would have been 36, right? We knew that because that's where he started with. He was at 36 feet high. At time 1/2, so at 30 seconds, half of a minute, would be about right here. And we can follow that up and be right about there, maybe 32 feet we could estimate. But that's just an estimate. We don't know that exactly. At time 1 minute, follow that one up. Maybe just a little bit less than 20, or maybe exactly, actually maybe it's exactly 20. It looks kind of exact there. But these are just what we think it is based on the graph. We can find the exact numbers using this nice neat equation. How do you do that? Well, we know t in our equation stands for the time, and h stands for the height. We can give those fancy letters instead of just x and y, which is what they used in this equation. So plug in what you know. Remember, these are the numbers we are estimating them to be at based on our graph, but we want to find the exact numbers, so we're going to plug in our time into our t equation. So when we have time at 0, we know this one's going to come out exactly 36 since that's where we started, and sure enough, 0 squared is 0, times negative 16 is still 0. That gives you the 36. So that one was perfect. What about when time is 1? Well, that'd be 1 squared would still be 1, so we have negative 16 plus 36, and that one's 20. So that one was perfect as well. The one we really aren't sure about, based on just looking at the graph, is the 1/2. So try that. We have negative 16 times 1/2 squared plus 36. Excuse me, 1/2 squared is 1/4. Negative 16 times 1/4 plus 36. Negative 16 times 1/4 is negative 4 plus 36. Oh, we actually did get it. It is 32. So now we know that it is exactly 32. We can get rid of that. But you might have looked at this graph and thought that was 33. So looking at the graph, sometimes they're not at these nice, neat points where we can tell exactly what they are. And that's the advantage of using the equation. Okay? Remember what an x-intercept is? It's where the graph crosses the y-axis. I'm sorry, did I say x-intercept? The y-intercept is where the graph crosses the y-axis. And very similarly, the x-intercept is where the graph crosses the x-axis. So in our chart, or in our graph, here is your y-axis. It crosses it at that point 36. So we could actually say our y-intercept is the point 0, 36. And because on a y-intercept, the x value always has to be 0, we can also just say that the y-intercept is 36. You don't have to give the full coordinates. The x-intercept would be right here. This red point right here. It's where your graph crosses your x-axis. That occurs in that point. The point of that, the y value, is 0. It's not up or down. You would need to figure out how many units over it is, and we can approximate this at about 1.5. And again, because your y is always going to be 0 for your x-intercept, we can just say the x-intercept here is approximately 1.5. In the future, not in this section, but in the future, we would be able to find that exactly by figuring out when h equals 0 and solving the equation. But we're not going to get into solving equations just yet, so we'll leave it as the approximation of 1.5. The point of intersection. Well, right now we only have one graph, but a point of intersection is where two graphs, two lines or curves cross. We can add the extra, the second line in, and that would be at that 1 foot where the water is. So let's make it blue. So at 1 foot, it's not a very straight line, pretend it is. At 1 foot, we have that extra line representing where the water is, and we could find that point of intersection right there. Okay, and in this case, that would represent where Professor Splash is hitting the water. We don't know what the x value is there. We could approximate it, maybe 1.4 seconds. But we definitely know what the y value is because we know that's at 1 foot. So this 1.4 is approximate. The 1 we definitely know. Story time. Submarine A is 900 feet deep and rises 50 feet per minute. Submarine B is on the surface level and submerges 100 feet per minute. Okay, so let's let this chart here be sub A. This T-chart over here will be sub B. Let's look at what we know. Submarine A is 900 feet deep, so that corresponds to a depth of negative 900 feet. That's where he is starting, so we can put that point. So at time 0, he's at negative 900 feet. He's rising, I'm talking about the submarine like he's a person. The submarine is rising 50 feet per minute. So if you look up here, our x-axis is in single minutes, and we want to rise 50 feet per minute. But over here on our y-axis, we are labeled in every 100 units. So to go up 50, we're only going to go up halfway in 1 minute. So our next point should go here. 50 more feet in a minute, 50 more feet, 1 minute, and you can continue that pattern. Okay. Submarine B is on the surface level. So if he's on the submarine B is on the surface, his initial position at time 0 would be 0. And then he's submerging, he's going down 100 feet per minute. So he's going down 100 feet by the next minute. 100 feet the next minute. Down 100 over 1. Down 100 over 1. Remember, we're working, we don't want to say the slope's down 1 over 1. That's not correct. It's down 100. It just so happens we're working in units of 100 on that y-axis. So think about how you're speaking mathematically and try to say things correctly. The slope is not down 1 over 1. The rate of change or the slope is down 100 over 1. Okay? All right, some things to talk about. We want to come up with an equation for this. So in the last section, we were just dealing with graphs. Now in this section, we're going to deal with some equations. These are both straight lines. We have the dots forming a green straight line and a red straight line. Straight lines can be modeled with the equation y equals mx plus b. Keep in mind what these mean. M is your rate of change, also known as your slope. B is your starting point. Where are you beginning? Also known as your y-intercept. Okay? So if we want to make equations out of these, we need to find two things. We need to find the y-intercept and we need to find the slope, the starting point and the rate of change. For sub A, y equals mx plus b, your starting point is very obvious. It's what? Negative 900. They said that's where he's starting, 900 feet deep. If he's rising 50 feet per minute, that's his rate of change, so it would be 50x. We don't need the plus sign because we already have a minus sign there, and we know a plus and a minus would just be a minus anyway. So your equation for this sub A is 50x minus 900. Using that equation, let's figure out what would happen at time 2. What would his depth be? Well, if you plug 2 in for your x, and we're leaving depth as y, you also could have called them t and d, that would have been fine. Plug 2 in for your x, 50 times 2 minus 900. 50 times 2 is 100, minus 900 should give us a depth of negative 800. Check that on your graph. Is that what we graphed at time 2? Sure enough, we're at negative 800. At time 4, according to our graph, we should be at negative 700. We can plug in 4 and see if we end up getting that. 50 times 4 minus 900. 50 times 4 is 200 minus 900 gives us a value of negative 700, which is what we expected based on the points we plotted. Okay, sub B, if we're working in y equals mx plus b, we want to find two things. We want to find our initial starting point, which is our y-intercept, and we need to find our rate of change, which is our slope. Starting position, your y-intercept, where does your green line cross your y-intercept? That happens at 0. And then your rate of change. Notice that with our red dots, we're increasing from left to right, so we had a positive slope. But for our green, we are decreasing from left to right, so our slope has to be negative. Negative what? You can think of this a couple different ways. You can look at it from your sentence, or you can look at your points. This is why I was emphasizing we don't want to say that this slope right here, we don't want to say this is down 1 over 1. If we said that, then we would say our slope would be negative 1. But it's not negative 1, it's negative 100. The reason for that is here we are not counting by ones, we're counting by 100s. So this would be down 100 over 1. And we know slope is rise over run. Rise over run, your rise is negative 100, your run is 1. So you get an equation of just negative 100x. You can drop off the plus 0. It's not needed here. So at time 2, plug in a 2 here. Negative 100 times 2 is, of course, negative 200. Check that point. Make sure your graph is correct. At time 2, negative 200, sure enough. And at time 4, you can plug it in to your equation. You'll get negative 400. Also, that's what we got when we graphed. What would the point of intersection represent here? We already said that the x-intercept, or I'm sorry, the y-intercept represents the starting points of the submarines. What would the point of intersection represent? The point of intersection here is where the two subs, I should say where and when the two subs are at the same depth. So at 6 minutes, both subs are going to be at negative 600 feet. So that's when they would pass one another. What would the x-intercept represent? The x-intercept represents when the submarine is at surface level, when it hits the surface, or here where it started at the surface. Okay? Next problem. We can use these methods to do story problems like we just did in the last two problems, or we can also use this to graph anything you want. So previously, we were able to graph using a t-chart. Using an x and a y column, you can choose any x values, plug them in to an equation, and figure out the y value. So if we take -5 and plug into our formula, or our equation, we're going to plug it in for the x. So we would have y equals the square root of -5 plus 5. I need to end my radical, my square root. Make sure the plus 1 is not under there because it's not in my equation. That gives me y equals the square root of 0 plus 1. The square root of 0 is just 0, and so I just end up with 1. My first ordered pair to plot is -5, +1. Okay, do it again. Do it with -4 now. Y equals the square root of -4 plus 5. Add 1 at the end. That would be -4 plus 5 is +1. The square root of 1 is just 1, and so I end up with 1 plus 1 equals 2. My next point to plot is -4, 2. Third number is -1. Y equals the square root of -1 plus 5. Add the 1 at the end. That's the square root of 4 plus 1. The square root of 4 is just 2. 2 plus 1 is 3. So -1, 1, 2, 3. Now, right now you might be thinking, wait a minute, why isn't that lining up? Because look, I'm going here 1, 2, 3. So why isn't that nice and neat in one straight line? And the reason is because look over here, you're -5, you're -4, but then you skip to -1. So they did not give us numbers right in order on our x values. Okay, plug 0 in. Y equals the square root of 0 plus 5 plus 1. Y equals the square root of 5 and then plus 1, but square root of 5 doesn't have a perfect, nice, neat answer. It's 2 point something, some ugly decimal. So this is the exact answer. We're just going to leave it that way, square root of 5 plus 1. But we can estimate it in order to graph it on our chart, on our graph. The square root of 5, like I said, is 2 point something. It's a little more than the square root of 4, which is 2. But not as much as the square root of 9, which would be 3. So 2.1, 2.2, somewhere around there. Add 1, we're at 3.1, 3.2. So we can plot it. It's just slightly above right there. But in our graph, or in our t-chart, we want to go ahead and leave it as the exact form. Pause the video, finish the last two, and go ahead and plot them. Okay, let's check our work. For x value of 4, you should have solved and got a y value of 4 as well. Plotted that point right here. But when you do -9, you run into a problem. And that problem is you have the square root of a negative number. At this point in your math lives, you are not able to have an answer for a square root of a negative number. So, we have a problem. What that means here is when x is -9, there is no y value for it. We say it does not exist. DNE, it does not exist. There will never be a point. Here's where -9 would be. There wouldn't be any point on that. And actually anything past -5 won't have a point. Okay? If you were to finish this graph completely, what would happen is it would actually start right here. There would be no points to the left of it. And it just does one of these. Okay, it keeps going up there. But you would not have any points further back to the left of -5. And again, that's because you cannot have a square root of a negative number. Okay? Story time. Timmy and Kat are at the arcade. The graph shows each person's quarters over time. So obviously the longer they're spending at the arcade, the less quarters they're going to have because they're playing games and spending them. So for Timmy, here's his chart. Kat, her chart will be over here. What are our variables? Your independent variable should come first, and remember that's your x value. Here, that's your time in minutes. So we're going to write time. It's being measured in minutes, and let's call that t. Your y value is your dependent variable. The number of quarters that Timmy has depends on how much time he has been at the arcade. So we have quarters, and the unit is just numbers, the number of quarters, and we can call that q. Of course, you can call it x and y, just being a little creative and using the t and the q. Before we keep filling out our t-chart, let's go ahead and see if we can come up with an equation. We obviously can see that these are linear, so we know we're working in that form y equals mx plus b. So we need to find two things. We need to find our y-intercept, and we need to find our rate of change, our slope. Y equals mx plus, mx plus b. But instead of b, what is Timmy's starting point? What is his y-intercept? Well, Timmy is, I did not label, Timmy is the red one. Well, I'm going to change it. Let's make him blue, since I already have written in blue here. And let me go back to using blue. So Timmy, his starting point is 30, so I can erase the plus b and I can make it plus 30. What is his rate of change? To find the rate of change, find two nice neat points on your graph. So we can obviously use this one. This one's not a great point to use because it's not it's in between 30 and 25. We want to use exact. Here is an exact one. So rise over run, rising, or in this case, you're going down. How many units? It's not 1. From 30 to 25, you were counting by 5, so it's down 5. And you're over, it's not 2. Look at what you're counting by. You're counting by 2, so this would be 2, and this would be another 2 for a total of 4. So I'm going to erase my m, and I'm going to make it negative 5 over 4. The last thing I can do is use the variables that we have written up here. Which one is your x? Is it t or q? Well, it's the independent, so it's this one. It's your x. And then we lastly can erase the y, and we can turn that into the q. So to fill in the rest of our t-chart, now you have the option. You can use this equation or you can use your graph. Oftentimes, it's easiest to use the graph if your points are at nice, neat, easy to read points and not at some random point in between. Like, for example, if you were trying to find at 15, that would be more difficult to do using your graph. That would be when you would want to use your equation. Let's see what we have here. At time 0, number of quarters is obviously 30. It's a nice, neat coordinate point. We can use that. At time 4, again, it's a nice, neat one. It's 25. And at time 14, it's in between, so we would want to use our equation for that. So if you plug 14 into your equation, you would need to then do some calculations. Q equals negative 5/4 times 14 should be negative 17.5 plus 30 is 12.5. And if you look, that looks to be about 12.5. Yep, halfway between the 10 and the 15. So our equation and our graph match up. Go ahead and take a minute and fill out cats. First, I want you to fill in the gray part, labeling the top of your T-chart, then come up with the equation, and then go ahead and finish your T-chart. Pause the video now. Okay, hopefully you have what I have here. Go ahead and check your work. She had an initial starting point of 40 quarters, so that's your y-intercept. And her slope, she went down 5 over 2. We're counting by 5s on your y-axis, 2 on your x-axis. That gives us our rate of change or our slope to fill in. These ones you could find them pretty easily off of your graph, but you also can plug them in into your equation. In this problem, what does the x-intercept represent? The x-intercept for each graph is where it crosses the x-axis. That happens, whoops, right here and right here. And what would that represent in this situation? It would represent when there are the time, so when 0, whoops, not tokens, we're working with quarters, when 0 quarters are left. So when they ran out of quarters. I put that for the y-intercept. That's your x-intercept. And then your y-intercept over here would be right there for this one and right here for this one. And in this example, that is how many quarters they started with. Number of quarters to start. And then lastly, the point of intersection occurs right here. That point is at 8:20, and that means at 8 minutes, both Timmy and Kat have 20 quarters left. So it's when they have the same number of quarters left. That occurred at 8 minutes and they had 20 quarters. Okay, that's it for you. Go ahead and continue on your packet into your practice problems.